All right, now we're in section 8. We're going to pretty much focus most of our attention. There is a little bit of a discussion at the end with troubleshooting redistribution, some great techniques and concepts that we can use to troubleshoot redistribution. But we're going to start this section here with a big discovery, and that has several different configuration issues that we're going to have to fix in the discovery lab, and redistribution is misconfigured. We already know what can happen if that's done, right? We can have routing loops, we can have suboptimal routing, slow connectivity for users. Routing loops can actually result in no connectivity as well. So we can fix those problems. So in this section, we're going to focus on how do we troubleshoot these issues. What are some of the issues that are related to specific routing protocols? So some issues that might exist in one protocol might not exist in others. What are some of the issues related to something called route feedback, which is basically redistributing routes that are already redistributed, invalid routing tables, routing loops, routing summarization problems, basic redistribution issues, and then suboptimal routing issues caused by redistribution. So we're going to go ahead and jump into Discovery 14, which is going to discuss all of these different concepts. All right, Discovery 14, troubleshooting redistribution issues. We're going to take a look at several different redistribution issues related to IPv4 and IPv6. As always, most of the configurations are already in place in our particular topology. Routing is set up, if you look at the diagram, it's a little bit complicated, right? Router 1 and Router 2 are EIGRP, and they're running named mode AS100 for V4 and V6. R2, R3, and R4 are running OSPF v2 for IPv4 and OSPF v3 for the address families. R4 and R5 are running EIGRP named mode for AS200 for both v4 and v6 address families. R5 is actually configured as an EIGRP stub router, and it's only advertising public prefixes from its loopback 1 interface into EIGRP. So we're actually adding kind of another layer of complexity here by creating this special router type. R5 has both v4 and v6 default static routes that point to its loopback. And that's really just to simulate the cloud, if you will, or some internet connection. R4 is also advertising into OSPF the public prefix, the v4 public prefix, and the v6 and v4 default routes that it's learning from R5. All right? R4 should not be advertising any other private AS200 prefixes into OSPF. So this is the scenario that we're faced with. Obviously, we're not going to try and tackle all the issues at once. Like I said in our previous section, we kind of have to look at each of these pieces individually and kind of break them down. All right? So throughout this discovery, we're going to troubleshoot and fix problems with redistribution. There are actually a total of 5 different issues that we have to correct, and each of them are unrelated to each other. And so we're going to solve them independently. All right? My suggestion is that there really is no specific process or procedure that you should use for troubleshooting any particular problem. To me, troubleshooting is about isolating primarily what the problem isn't as opposed to what the problem is. So you eliminate the possibilities and you limit the scope of the problem by eliminating those possibilities. Now, you could do top-down troubleshooting where you're troubleshooting from the application layer down to the physical layer. In the case of IP connectivity and routing, it's better to really focus on what we call a divide and conquer approach, or what I like to refer to probably inappropriately as the split the baby approach, right? We start in the middle and we kind of work our way in one direction or the other based on what we think the network should be responding like and so on. So a ping test, for example, would be a divide and conquer approach because ping is a layer 3 protocol. We're not testing layer 8, we're not testing, layer 7, we're not testing layer 1 or 2. We're going right to the middle and kind of trying to troubleshoot from the middle. We can also do a follow the path. Ping is kind of like that. Traceroute would work as well. to isolate the problem by eliminating the potential problems along the path. What path does a particular packet take as it's moving through the network? If a ping is failing, can we isolate the location of that failed ping and so on? All right, so the redistribution piece in this topology, R2 is performing two-way redistribution. If you look at R2 in the diagram, kind of makes sense. R2 is part of EIGRP and OSPF. It's redistributing between EIGRP AS100 and OSPF for both V4 and V6. R4 is also performing redistribution. Makes sense. It's connected to EIGRP AS200 and OSPF. It's also doing two-way redistribution between AS200 and for both V4 and V6. All right. R5 in this particular case is performing redistribution of its default static routes. So it's not necessarily participating in two routing protocols, but we're redistributing static routes into EIGRP. So those will still come in as DEX routes. All right. So that's really how it's supposed to look primarily. All right, so we got 5 tickets that we're going to try to solve, and all of these are related to redistribution, so we'll kind of break these down. In the first ticket, the description of the ticket is that R1 is not receiving any of the external routes. All right, R1 is all the way over here in EIGRP AS100. Those external routes are coming from R5. According to our network specifications, which we outlined in the beginning, R2 should be redistributing from OSPF into EIGRP for both V4 and V6. So we have to fix this problem. Now, what do you think the first step is going to be? Let's find out who has the default route and who doesn't, right? We know R5 is the one that's originating the default route. And I could simply go to R5 and make sure R5 is redistributing the route. That could be certainly my first step. But to me, that's not necessarily the best first step. To me, the best first step would be to maybe possibly see if there is another router along the path that has those default routes. So again, I'm kind of trying to do a divide and conquer approach as opposed to doing a beginning to end type of troubleshooting. I'm just trying to save a little time. So I would say, okay, we already know that R1 is not getting the default routes. Maybe let's see if R3 is getting those default routes. So I'm going to go into R3, and because that's kind of in the middle of the network, and I'm just going to do a show IP route. And R3 does not have the default routes. So I've already kind of isolated the problem to this half of the network, because if R3 doesn't have a default route, then R2 is not going to have a default route. See what I'm saying? So I can work my way back and I can say, okay, does R4 have a default route in this particular case? Show IP route. R4 does not have a default route. So I've already saved myself quite a bit of time by kind of going through and saying, okay, does R4 have a route? Does R3 have a route? Now, if R4 doesn't have a default route, now I can kind of go back and say, okay, well, should I look at R5? There's a couple of things that we can do, though, to be able to troubleshoot this. I could say, all right, let's see if I have a neighbor relationship with R5. Because if I don't have a neighbor relationship with R5, then how can I actually learn the default routes? Now, I do see an EIGRP route here. So that, and it already says 45.5. So I'm pretty sure that I have a neighbor relationship with router 5. So I've eliminated kind of that problem. Now, if I didn't have a neighbor relationship, then I could do some pings. I could maybe check my EIGRP configuration to see if I don't have a relationship with router 5, maybe it's a shutdown interface or whatnot. But the reality is that I have that reachability. Now in the book, they kind of had us starting at R1 and working our way back. Do a ping to R2, make sure you have a relationship with R2, do a ping to R3, make sure you have a relationship with R3, and so on. I don't think that's necessary. I think what's more important is that we are able to kind of isolate the problem. And by saying, okay, I don't have the default routes on R4, if I don't have the default routes on R4, there's no way those default routes are going to get to R3 or R2. So now I really have to identify what the issue is on R5. All right? We know that we have an adjacency, so let's go to R5 and see if there's any kind of indication, show run pipe section EIGRP, indication of why the default routes are not coming in. All right? So I see here EIGRP Cisco. I see the address family for V4. We have EIGRP stub connected and summary. We are redistributing static routes. So if I do a show run pipe include route, show run pipe include route, I can see that I do have the default static routes. I actually see a couple of problems here, but I see what the primary problem is. The stub configuration. EIGRP stub connected summary means redistributed routes are not going to be advertised. So one of the ways that we can verify this is to use show IP EIGRP topology. And if I can see the default route in the topology, I know it's part of the EIGRP process. But I am not sending that information to my peer because of my stub configuration. So let's fix that problem first. Let's go into router EIGRP Cisco. We're going to go into our address family for IPv4. All right? And I'm going to go into my global process. This is not under the topology base. The redistribution is fine. We know it's in the EIGRP topology table, so we know it's part of the EIGRP. I just have to come in here and do my EIGRP connected summary and static. You could do redistributed also because this happens to be a redistributed route. All right? So far, so good? Now, that doesn't necessarily mean it fixes our problem. But let's go to router 4 and see if router 4 is now receiving a default route. It is. It's coming in as DEX. Great. Now, let's go to router 2 and see if it's receiving a default route. Show IP route. And sure enough, it's receiving a default route. Doesn't mean we fixed our problem because there's a redistribution point here. So let's go to router 1 and see if we have a default route. Show IP route. We still don't have a default route on router 1. Okay? In fact, we're not really getting any routes on router 1 at all. All right? But we've at least confirmed that the V4 default route is making its way all the way to router 2. Now, router 2 is redistributing routes from OSPF into EIGRP and vice versa, from EIGRP into OSPF. So we need to look at the configuration of router 2 and make sure that that redistribution process is applied correctly. Show run pipe section router. Well, let's do EIGRP for now because we're troubleshooting in one direction. All right. Router EIGRP Cisco. Redistribute OSPF. There is a problem. We are redistributing OSPF into EIGRP. What is the issue? And this goes to your understanding of the rules of redistribution. We've broken a golden rule. And that golden rule is when you redistribute into EIGRP, if you don't specify a seed metric, the routes will be infinite. Right? We redistributed from OSPF 10, which is the correct autonomous system number or process ID. Well, we have to actually see, I'm assuming it's the appropriate process ID. Let's do a show IP protocols real quick. Show IP protocols. And it is process 10. But the redistribution doesn't apply a seed metric. And as such, the routes they get redistributed, but they are unusable. So we need to fix that by going into our EIGRP process and going into our address family. Remember, we're only focused on V4 right now. We'll have to go back and check V6. Go into our address family, and then under our topology base, go into our redistribution, and we can either do a default metric or we can apply a metric directly. 10,000, 100, 255, 1500. I'm picking arbitrary numbers here because it doesn't really matter. It's a single point of redistribution, so it doesn't really matter what the seed metric is in this case. Again, if you had multi-point redistribution and mutual redistribution, you'd have to kind of consider those scenarios as well. But do we have a default route? Yes, we are now getting a default route, and we're getting those other DEX routes that we should be getting as well. Okay? So it was actually a couple of different issues along the way that we had to solve to fix that particular problem. All right? Infinite metric is a problem. I don't know that the book necessarily, in our case, the book necessarily had multiple issues, but in this topology we had multiple issues, so that's something we definitely had to fix. Now let's take a look at V6. Show IPv6 route. I do not have a default route for IPv6. So just because we solved the problem for V4 doesn't mean we solved the problem for V6. And I'm going to treat this as a completely different stack. I'm going to treat this as a different stack, which means that I'm going to do the same thing I did before. I'm going to split the baby. I'm going to go into the middle of the network, and I'm going to see if router 3 has a default route for IPv6. Show IPv6 route. And router 3 does not have a default route. So now I'm going to go to router 4. Kind of working my way back. I'm going to go to router 4, show IPv6 route. Router 4 does not have a default route. I'm also not getting any EIGRP routes from router 4, on router 4. So a couple of things could happen here. I could do a show IPv6 interface brief. There's lots of reasons why I might not be getting that default route. And you could certainly use what we call a shoot from the hip approach. Shoot from the hip approach is a scenario in which you, based on your experience and things you've seen in the past and whatnot, you think it might be related to this or that, so you immediately go and troubleshoot those particular problems. Maybe their symptoms are congruent to what you've seen in the past for other problems. So you might use the shoot from the hip. Show IPv6 interface brief. I want to make sure that the interfaces that go to my other peers are up. We do see that they're up. Show IPv6 EIGRP neighbor to see if I have a neighbor. Oh, I don't even have a neighbor on router 4. Well, that's a bit of a problem. I should have a neighbor between router 4 and router 5. What could cause my neighbor relationship to fail? Maybe it's a mismatched autonomous system number. It is AS200. That is AS200. Let's go to router 5 and see what router 5's perspective is. Show IPv6 EIGRP neighbor. So it's AS200. How about show IPv6 EIGRP interface brief? interface, excuse me. OSPF, we use the brief option. What does this command show me? It shows me that I'm running EIGRP on Ethernet 1.1. If I do the same thing on router 4, show IPv6 EIGRP interface, I can see that I'm actually running EIGRP on 2 different interfaces on router 4. Am I supposed to be? I don't think so. I should really only be running it on 1.1. Why is it running on 1.0? That's a bit of a problem. But I am running it on 1.1. It should not be running on 1.0 though. Interesting. So EIGRP should be running on 1.1, but it should not be running on 1.0. Okay. Let's solve the relationship problem on 1.1 first, and then we'll figure out why it's running on 1.0 later. My next thing is going to go look at the configuration for EIGRP specifically and see if maybe I have passive interface. We know it's already running on the interface. We know EIGRP is already running on the interface. So let's see here. That's a problem. The EIGRP process is shut down. So that's clearly going to be a problem. Let's fix that problem. We need to turn on the process. No shutdown. There's our adjacency. Okay, so again, these problems aren't necessarily directly related to redistribution. I don't think the intent of this exercise was to have these other problems, but it's kind of nice because we get to see some of these other issues that we might have to troubleshoot. This is probably just a result of poor configuration in general. There are certain commands that weren't applied that should have been applied, but certainly that's going to be that. Let's check router 5 too, just to make sure. Well, we got an adjacency, so we know the EIGRP process must be running on router 5. I guess the next step is to see if we have that route. Do show IPv6 route. And I still don't have a default route. I still don't have a default route. But I do have a neighbor now. Do show IPv6 neighbor. And I do have a neighbor. I actually have 2 neighbors. Again, I don't understand why EIGRP is running on this interface. It should not be running on this interface. And I think we can't really control what interface EIGRP for IPv6 runs on. We could make the interface passive. But router 3 should definitely not be running EIGRP at all. And I think that's a misconfiguration as well. Let's check to see if router 3 is configured with EIGRP. Let's do a show IP protocols. It is not. That is really strange. Show IPv6 protocols, sorry. Well, it's only running OSPF. So what am I looking at here? Ethernet 1.0, Ethernet 1.1. Based on the topology diagram, this is Ethernet 1.1, which is correct, and this is Ethernet 1.0, based on the diagram anyway. Yep, that is correct. R3 1.0 to R4 1.0. So how could I have a neighbor there if R3 is not running? Oh, you know why? This is not related to EIGRP. I didn't put EIGRP in here. This is my ARP cache. Well, the equivalent of my ARP cache. Silly me. All right. Show IPv6 EIGRP neighbor. All right, there we go. That makes more sense. I forgot the EIGRP. It's been a long day. So I forgot the EIGRP, so we were looking at the neighbor discovery protocol. We weren't looking at EIGRP, and this makes sense. We have one neighbor. But we're still not getting that default route. I know that for sure. All right. Another thing I could do with regard to redistribution, and this is really, really helpful, whenever you redistribute anything into EIGRP, it should show up in the local topology database of that particular router. So if I do a show IPv6 EIGRP topology, I should see that default route in the topology database, which tells me that redistribution is working locally on that router. It is being redistributed. :/0, it is being redistributed. So, do we have the same problem that we had in IPv4 with the stub configuration? Show run pipe section EIGRP, and let's see if we have the same problem. Yes, we do. Under the IPv6 address family, we're stub connected in summary. So we'll go ahead and fix that problem, and we should be good with this particular ticket. I'm going to go into EIGRP, address family. This shutdown, by the way, kind of stands out, but what that means is that we've shut down EIGRP on that interface. So remember, with IPv6, by default, as long as the EIGRP process is turned on, it automatically runs on all of the interfaces. So by issuing the shutdown command under the AF interface configuration mode, we're saying do not run EIGRP on this interface. It doesn't mean that the interface is shut down. It means that the EIGRP process for that interface is shut down, which it should be, by the way. It should be because, why? Because that loopback is supposed to represent our connection to the internet. So we should not be running EIGRP on that interface. But we should be doing EIGRP stub connected summary static, just like we did with v4. All right? So now I'm going to go all the way back to R1, and I'm going to see if I have a default route. It might take a minute to propagate. If it doesn't propagate, it could be related to something completely different. Doesn't appear to be propagating. So we need to see where the issue lies. Let's go to router 3 and see if it's on router 3. We are getting a default route on router 3 now. It's actually tagged. So the redistribution process is applying a tag. So let's go to router 2 and see if we're getting it on router 2. Show IPv6 route EIGRP. Let's just do show IPv6 route. We are getting a default route on router 2. So it really should be showing up on router 1. There must be a redistribution problem. Because again, the default route shows up on router 2. Router 2 is responsible for doing the redistribution. Why would the default route be excluded from that? So now we need to investigate the redistribution on router 2. Show run, pipe, section, and it's coming from OSPF into EIGRP. So we want to look at the EIGRP section and specifically the redistribution. And here's the problem again. EIGRP is shut down. All right. So it's not necessarily directly related to EIGRP, to redistribution. It's directly related to the fact that EIGRP for IPv6 is turned off, so redistribution is not going to work. Redistribution is not going to work. So we need to turn that on. So let's go into our EIGRP process, address family v6 unicast. and do a no shut. All right. And we got our neighbor on Ethernet 1.0, which is this link here. That's good. Now I'll bet if we go to router 1, we will see that default route. Still don't see the default route. We're seeing an EIGRP route, but we're not seeing the default route. Which EIGRP route are we seeing? We're seeing the 1023 network, which we shouldn't be seeing as part of EIGRP. How do we fix that problem? We just saw that on the other router. Remember, when you enable EIGRP for IPv6, it automatically enables it on every interface. We need to suppress EIGRP from running on Ethernet 1.1, so we need to go into AF interface Ethernet 1.1, AF interface Ethernet 1.1 on router 2. All right, 1.1, and we're going to just shut down EIGRP on that interface. It's not related to our problem, but again, we shouldn't really be running EIGRP on that interface because it's part of OSPF. So now if I go back to router 1, I shouldn't see any EIGRP routes except for the default, but again, the default is not coming in. So we have kind of a whole kind of slew of problems in this configuration, but that's the idea, is that we kind of walk through the network, we make sure it's configured the way it is. This is what you have to do in the CCIE troubleshooting portion. So let's go back to router 2 and look at our redistribution process. Do show run section EIGRP. And specifically, we're looking at the redistribution process. Remember, we're redistributing from OSPF into EIGRP. From OSPF into EIGRP. Actually, let's do section router. That's going to be a cleaner grep. I'm noticing some other stuff down here. Here's the OSPF stuff. We're not worried about that. Redistribute EIGRP 100. That's interesting. Include connected. That's a completely wrong statement, isn't it? Sorry, that's OSPF. Let's go back up to EIGRP. That is correct for OSPF. Scroll up, here's the EIGRP section. We have the same problem that we had before, which is what? Well, we fixed that problem already. That was on router seed metric. We don't have a default seed metric, which means the metric is going to be infinite. So we need to go back into our address family here, and we need to go under our topology base, and we have to specify a seed metric. So metric 10,000, 100, 255, 1, 1500. Again, it doesn't matter what numbers you're picking here because it's only a single point of redistribution. Now we go back to router 1, and now I should see that default route, which I do. Okay? Whew. So we fixed the first ticket. We fixed the first ticket. All right. Remember, the first ticket was all about those default routes. There's probably already, obviously, other things to be concerned with. Router 2. Let me do a show run, section router. Redistribute OSPF, and then I specified the metric. That's what fixed that problem. We shut down EIGRP on interface 1.1 because there's no reason to run it there because that's an OSPF interface. All right. Traditionally, we would limit the scope of the protocol by using network statements that include only the interfaces that we want. But in this case, it's IPv6, so it's a little bit different. Okay. So we have fixed that problem. Now, we used a lot of different techniques in this case. There's certainly other commands that you can use. Show CDP neighbors, show IP interface brief. We could have done some pings. We could have done, looked at topology tables and routing tables. And there's no right or wrong way to troubleshoot. Certainly the goal is to get to the solution as quickly as possible. But ultimately, our goal is to solve the problem that we were faced with, which is that the route wasn't showing up, the default routes were not showing up in the routing table. All right? Now, let's see, do we have any other things that we need to solve? So I think we actually went through and solved all the problems, but you know what? Let's just do one final check. I don't think we had any other restrictions. If we go back and look at our original requirements, the original requirements stated that we're doing two-way redistribution and the default routes are being redistributed. But it does say that in our requirements, R4 should not advertise any other AS200 prefixes into OSPF, only the public prefix and the default routes. So if we look at the diagram, R5 is here, and the R4 is here. So this 45 subnet should not be advertised. The 172.45 v6 prefix should not be advertised. Only this public route, 201 and 165, and the default route. Even this loopback should not be advertised. All right. So let's go to R1 and do a quick show IP route. Show IP route. And we are only seeing one external route. That's good. So it looks like that's working. I'm not seeing, but I am not seeing some of the other routes. The external routes I'm not seeing. The public prefix. It's not really a problem in this case because we have the default routes that get us to the public prefixes anyway. So I'm guessing on router 5, we're doing redistribute static, not redistribute connected. So let's see if R5 has other static routes. Show IP route static. Yeah, it only has the one static route. Show run pipe include IP route. Yeah, it just has the one static route. I'm not sure if they intended for those other routes to be advertised. I don't think they're necessary because it's a default route. All right? I don't think it's necessary to advertise those. That was really the only requirement. If we look at the redistribution, we know what the redistribution process is on R5. Let's look at the redistribution process on R4. Show run pipe section router. The redistribution process on R4, redistribute OSPF, so we're not applying any filters in that direction into EIGRP. What about into OSPF? Here we go. We're redistributing EIGRP based on the route map EIGRP routes. So that's the filter that allows us to filter out those internal routes that are being redistributed. If I do a show run pipe section route map, I should see the EIGRP route map. And it is saying match IP address 10. It's got to deny though, which is really interesting. Because there's an implicit deny at the end. Let's look at access list 10. Section access-list. And it's matching the 145 subnet. So I'm very curious actually how the default route is actually getting into OSPF if we didn't explicitly permit that default route in. Because remember, the route map has an implicit deny at the end. So if something is not explicitly permitted, it will be denied. I would have expected to see a kind of a permit all at the end for everything else, because they're just filtering out this 45 subnet in that process. Let me see if they're applying that to v6 as well. They're probably using a different access list for that. Show run section router. And under the EIGRP process, they're doing a default information originate. Got it. So what's happening, this is definitely not the cleanest way to do this. It works, but it's really not necessary. When you have a redistribute statement that references a route map that has no permits, nothing gets redistributed. So we would have been able to solve the same problem or create the same scenario by just simply not redistributing. Our route map has no permit statements. So nothing is getting redistributed. So the reality is that redistribute EIGRP 200 command doesn't really do anything because the route map is all deny. Even the access list that the route map references is all deny. The only reason we're getting a default route is not through redistribution. It's because we're doing a default information originate. So what if we wanted to fix this problem? I'm not saying that it's a problem. We're still getting the default route. But what if we wanted to fix this particular problem and actually use the route map to send the default route, but not the 45 subnet? First thing is, let's get rid of the default information originate. Oops. Router OSPF 10. No default information originate, which means we should lose the default route on router 1. And we did. All right, but now we want to get that default route back, but through the redistribution process. So we have this route map. If I do a show run pipe section access-list, I'll see the access list that's blocking the 45 subnet. All right? It's actually permitting the 45 subnet, which is then being denied. So what I really need to do is permit the default route and deny the 45 subnet and then change my route map. So I'm going to do no access list 10. And I'm going to say access list 10 permit 0.0.0.0.0.0.0, which is my default route. Forgot an S there. And then access list 10 deny this network. So I'm permitting the default route, which is already part of EIGRP. We know that's the case because we fixed that. And I'm denying that network. Now if I do a show run section route map, I have to fix my route map. Because the route map is denying 10 and matching the address, and before the access list was just permitting this 45 subnet. So if I were to delete the route map completely, it would mess up this command here. So what I'm going to do is I'm going to do a route map, EIGRP routes, permit 5, and I'm going to say match IP address 10, and I'm going to do no route map, EIGRP routes, deny 10. Now, technically, I didn't really need to do this command because there's an implicit deny at the end of every access list. I could have done that, could have eliminated that, but it shows me when I'm looking at the running config what my objective was, and that's why I put it in there. It doesn't technically need to be there because of the implicit deny. So the only thing that would be permitted would be the default route, and I should have a default route back, which I don't. So that's good. We get to troubleshoot some more. Why the heck do I not have my default route back? Let's do a show run pipe section router. And we're talking about OSPF, redistribute EIGRP 200 subnets, route map EIGRP routes. Let's make sure that the default route shows up here. It does. It's learning the default route via 45.5. So it is in EIGRP. We know it's being redistributed because it's coming in as DEX. So the question is, why is it not being redistributed into OSPF? Do show run pipe section access dash list. Permit 0000. And deny 172.16.45, which we don't really need. So we're permitting the default route. We're denying everything else. Do show run pipe section router. No, route map. EIGRP routes. I'll make sure I spelled it correctly. EIGRP underscore routes. Permit 5. Match IP address 10. This is access list 10. It's a permit statement. We're matching access list 10. And I'm wondering if it has to do with the fact that access list should work though. Do show run section OSPF. And we're redistributing EIGRP 200 into OSPF based on route map EIGRP routes. Seems like it should be working. Let's see if router 3 is getting a default route. We lost it from the default information originate. Show IP route. But let's see if it's getting it. It's not getting it. How about let's see if it's in the OSPF database. Show IP OSPF database. It should show up as a type 5, and we're only getting one type 5, which is not the default. So it's definitely not being redistributed. All right, let's do it this way then. IP prefix list, default, permit 0000/0, which is the default route. That's really the only thing that we're trying to redistribute. And route map default, permit 10, match IP address prefix default. All right. And router OSPF 10. Redistribute EIGRP 200. Make sure it's the right autonomous system number. Well, no, we don't reference it there. We reference it here. So it is AS200. Based on route map, default. Subnets. Because we are using classic OSPF, we're not using OSPF v3. So we need the subnets keyword. So now if I do a show IP OSPF database, I should see a type 5 route for the default route. Why is it not going in? Why is it not going in? I should be originating. Let me do self-originate. Show IP OSPF database, self-originate. I should be originating that default route into OSPF. I don't know why I'm not. Do show IP EIGRP topology. It's there. Inside of EIGRP. It is in the routing table as a DEX route. So I'm not quite sure why this default route is not being sent in. I went ahead and I removed the reliance on the route map just to make sure I wasn't having an issue with the route map. And I just did redistribute EIGRP 200 subnets. Show IP protocols. It is EIGRP 200. We don't have any filtering set up. We're redistributing into OSPF. But we're not. And do show run, show IP EIGRP topology. The default route is in EIGRP. Do show IP route. The default route is in the routing table. But if I do a show IP OSPF database, I'm not seeing the type 5 coming in for that default route. So I'm not sure what's happening in this particular case. I thought it may be related to maybe the fact that this area might be configured as a special area type, but it's not. We don't have any special area type configurations applied. Do show run section router. OSPF, this is not applied as a special area type. Let me let me take away this route map and let's go to router OSPF 10. I thought I had removed that. So let's do no redistribute EIGRP subnets route map. And let's just do redistribute EIGRP 200 subnets. And let's see, do show IP OSPF database. And see what we're seeing here. So we are now seeing the other prefixes that were not supposed to be there originally, but I'm still not seeing the default route, which is really, really interesting. Show IP route. So this D route is going in, and this DEX route is going in, but for some reason, the default route is not going in. And the only thing I can think of is that it's a DEX route. So maybe somebody can send an email or post a comment if you understand why this default route is not going in. The solution, of course, would be just to originate a default route in OSPF like they had originally, but I just, for the life of me, can't figure out why that DEX route is not being redistributed. I could see why if it was a special area type, but it is not, so not quite sure. All right. But we're reaching our limit on this video anyway, so we will go ahead and wrap up this discovery, and we just have one more brief section that we're going to go through, and then we'll wrap up this section. All right, so in our next section here, we're just going to wrap up this section 8 by talking about troubleshooting. We did our discovery just now, and now we're just going to kind of wrap up with some discussion. The one thing that I had talked about, which I think perhaps is probably the most critical thing when you're doing redistribution, is that you make sure that the routes that you want to redistribute exist in the router that's actually performing the redistribution, because a router can only redistribute what exists in its global RIB, or the global routing information base. So that's a really important concept, and that's when we started each of our redistribution discoveries. That was the very first thing that we checked, is did the routes exist in the local router? If routes are not being redistributed, and they do exist in the local router, make sure that the route map is configured correctly. Like I said, when you reference a route map from the redistribution statement or the redistribution process, if you've referenced a route map that doesn't exist, or if that route map doesn't have any permit clauses, it's not going to redistribute into the other routing protocol. In the case of distance vector, we have to have a seed metric defined because the default seed metric is infinite. And again, like I said, routes that do not exist in the local routing table cannot be redistributed. So that's a loop avoidance mechanism, if you will, that's built into the routing protocol. Also, if you have redistribution and it's working correctly, but you run into a scenario where you have suboptimal routing, or you've created some sort of routing loop, we talked about doing route tags to filter or control the distribution policy. We talked about modifying perhaps administrative distance values when you redistribute from one protocol to the other, namely when you're dealing with EIGRP, particularly because EIGRP inserts routes with an AD of 170, the DEX routes. So again, it's a matter of kind of going through and verifying that everything is appropriately configured and you've checked all the boxes, if you will, for that redistribution process. If routes are not redistributing external routes, we saw that actually yesterday in our discovery, make sure that you're referencing the appropriate routing process. Maybe you've referenced the wrong autonomous system number. Maybe you've referenced the wrong process ID for OSPF. Make sure that your access lists for classification are correct. Make sure your route map commands are correct, and so on. All right. We also talked about the fact that routes that get redistributed from another routing protocol, in some cases, have to be updated with the metric that's understood by the receiving protocol. That's what we call our seed metric. And in a lot of cases, unlike OSPF, where that seed metric is globally defined, in the case of EIGRP, for example, that seed metric is not predefined. So redistribution won't take place. Technically, I guess the routes are being redistributed, but they're not going to be usable because they're going to have an infinite metric. All right? Be aware that, like I said, only routes that actively exist within the routing table are going to get redistributed, so make sure you check your routing table. And again, the original information that's being captured from the route itself is going to be lost in the redistribution process. So there is no guarantee that you're going to have a loop-free topology when you're doing this redistribution. That's why you need to make sure that you control that possible looping of routes with filters and tags and so on. All right. Now there are some additional rules that apply in the design concept. Number one, the router should always prefer something internally over something externally. OSPF does that automatically, right? There's an order of operations within OSPF that says, I'm going to trust my OSPF routes, my intra-area routes, more than my inter-area routes and more than my external routes, all right? And you would never, ever want to redistribute a route back into a domain that the route came from in the first place. So again, that would require the use of a route map where you can do tagging and you can ensure that you're filtering routes being redistributed based on that tagging information. All right, and we saw an example of that actually. They have another example here in the book, but they're doing router EIGRP 100. We're redistributing OSPF into EIGRP based on route map, etc. They do have a default seed metric applied, so we know that that's going to work. But if you look at the route map, we're denying anything that has been tagged with 33, and then we're permitting the remaining routes. So we can assume that if it's tagged with 33, that was a route that was already redistributed from EIGRP into OSPF at another point in the network. And then anything that's not tagged would be the routes that are originating from the OSPF process 1, and we're going to go ahead and tag those routes with a tag of 44. Again, the tags are somewhat arbitrary. They don't necessarily mean anything. It's just a kind of an arbitrary value that you select as an administrator. But it's nice, like we did in our exercise, maybe select a tag that gives you some indication about where that route is coming from, or potentially who is responsible for redistributing that route. All right. Now there are some protocol specific things to consider as well. Static and connected routes will have different administrative distance assigned. A static route, for example, will have an administrative distance of 1. Connected routes typically have an administrative distance of 0. When you have the redistribute command, protocols like EIGRP, which has the ability to distinguish between an internal route and an external route, that protocol is going to redistribute static and connected routes as external routes. So they're going to come into EIGRP as a DEX route. If the network command was used to insert a route or inject a route into EIGRP, we know that route is going to show up in EIGRP as an internal route within the IGP protocol itself. All right, just to refresh, EIGRP, unlike OSPF as an example, does not automatically have a default metric for any of the learned routes. If the default metric or a manual metric is not specified, and the difference there is the default metric is we're using that default metric command, which applies to any redistribution process, as opposed to manual metric, which is a metric applied directly to the redistribution process. EIGRP will assume a metric of 0, and it will not advertise those prefixes. Also, EIGRP will not auto-summarize external routes unless you have a connected route or an internal EIGRP route in the routing table from that same major network of the external routes. So, for example, if I'm redistributing maybe 20 or 30 external routes, and they're consecutive routes, I cannot summarize those consecutive routes unless I also have an internal route or a connected route that's part of EIGRP that falls within that same scope. So if it's network 10.10.0.0, 10.10.1.0, 10.10.2.0, 10.10.3.0, those are all DEX routes coming from an external process. I cannot summarize those 4 networks by themselves. If I somehow include a prefix that's in the routing table from an internal routing process, a D route, or I include a connected route, then the summary can be generated. All right? So that's a kind of a little caveat that you have to consider. If the EIGRP stub router needs to redistribute routes, we have to do the stub redistributed, right? And that can actually happen in a couple of ways. If we're redistributing static routes, and we can use the stub static command, because stub static means static routes that are redistributed. If it's a routing process like redistributing from OSPF or redistributing from BGP, then we would need the stub redistributed command. Okay? With OSPF, we use the keyword subnets when we're redistributing classless networks into OSPF. So when we're redistributing routes into OSPF, only routes that are not subnetted are redistributed if you don't use that subnets keyword. The exception to that rule is if we're using OSPF v3, and we talked about that yesterday. OSPF v3 automatically assumes classless, so we don't necessarily need that subnets keyword. If it was OSPF v2, we would definitely need that subnets keyword. All right? We have maybe a situation that could arise, for example, when connected or static routes are being redistributed in or out of OSPF. There are some other rules that apply. The subnets keyword has to be entered when we're doing the redistributed, when we're trying to redistribute classless networks into OSPF. It doesn't hurt to have the subnets keyword even if it's not necessary. So if you run into a situation where you're redistributing into OSPF, the best rule of thumb is to just go ahead and use the subnets keyword because it's going to include classful and classless networks, and then you're covered, right? You don't have to worry about whether or not you're supposed to have the subnets keyword or not, okay? So I might say, for example, in OSPF, redistribute static, but I'm going to add the subnets command to redistribute the static routes in OSPF. All right. Now, the default route, and we ran into this as well, is not going to be injected into OSPF. If you want to redistribute a default static route into OSPF, the only way that you can do that, and this is the problem that we were running into in Discovery, is with the default information originate command. So the default route is a unique exception to the redistribution rule, even if that default route is being learned from another process. All right? We struggled with that issue in OSPF yesterday in our Discovery. All right? OSPF stub areas, totally stubby or stub areas are not going to allow us to redistribute external routes because type 5 LSAs are not allowed in those areas. But we could get away with that if we made it a not so stubby area and we could generate type 7s within the area, but type 5s are never allowed. We talked about that as part of our OSPF discussion. One of the functions of a type 4 LSA, remember that was our ASBR summary LSA, is to announce the reachability of the ASBR to other areas, not within the same area that the router exists. So if you have an AS, like we did in our topology in our previous Discovery, if you have an ASBR in the same area, you're not going to see the type 4 because we use the type 1s to reach that particular ASBR. So the ASBR itself doesn't generate the type 4s. That's the responsibility of the ABR that is connected to the area, and then those type 4 LSAs go into the other areas that the ABR is attached to. All right? To generate a summary LSA, type 3, or to generate a type 4, we have to have a connection to other areas. And again, special area types are going to restrict what types of routes can go into that particular area. External routes are not allowed into any special area type as a type 5. Only type 7s are allowed in a not so stubby area or a totally not so stubby area. With regard to BGP, even though it's not really listed here, if we're redistributing static and connected routes into BGP, it's very important that you apply filters. You don't want your BGP autonomous system number to act as a transit AS, especially if you have connections to multiple ISPs. So there are specific filters, and we'll see that in our BGP discussion, that you would apply in a redistribution process. If BGP is redistributed into an IGP, into an interior gateway routing protocol, only the eBGP routes, not iBGP. And again, we'll talk about the difference between eBGP and iBGP when we get into our BGP discussion. But eBGP routes are basically routes that are learned from another BGP autonomous system number, not within our own BGP autonomous system number, but only those eBGP routes that are going to be learned are going to be redistributed. Anything learned through iBGP should also be known by your regular IGP routing protocol, so there's really no need to redistribute iBGP routes into an IGP protocol. We assume that if it's an interior route, that somehow that interior route is being learned by the IGP protocol as well as maybe possibly iBGP. All right, so redistribution of iBGP into IGP is disabled by default. If you run into a specific scenario or a specific case where that's necessary, where you actually have to do that, you can do the BGP redistribute internal command that will override that behavior, that will allow the redistribution of iBGP routes into IGP, but you need to make sure that you're taking some sort of precautions in that particular regard. All right, so those are just some of the rules that we have to be concerned with. Now, with regard to checking relevant information, certainly looking at your routing table is probably the best option, not only prior to doing redistribution, but post-redistribution, because obviously the routing table is where you want information to go. I would say, in addition, it can be beneficial to look at topology tables as well, because again, if something doesn't exist in the topology table, that means it basically doesn't exist in the protocol and it can't be redistributed. So we saw that in the discovery where I was looking at the topology information just to make sure that topology information existed or the routing information existed in the topology table. It may not always go into the routing table, but again, if it isn't in the routing table, it's not going to get redistributed anyway. We only redistribute routes that we're using, not all the routes that we've learned. So the stuff we learned goes into the topology table. The stuff that we're using goes into the routing table. But looking at the routing table is very useful. We saw in our discovery too, if you look at a specific route, so say for example, instead of just doing show IP route, you might do show IP route 10.2.0.0, you can get additional information about that route. We saw where we could see how the route was being learned, but other sources of that routing information. We could see the route tag and so on. We could see the metric information if we were trying to verify or check the seed metric information for that particular route. If you're using route maps to filter redistribution or you're using route maps to control the redistribution process, show route map would be a good command. If you're using prefix lists, show prefix lists, access list, show access list. Just want to kind of step through the process, right? A prefix list or an access list is something that you define that allows you to classify particular types of things that you're redistributing, and then the route map references those prefix lists and access lists. So that would be something that you would want to check as well. Show IP protocols, maybe, could be kind of useful, right? You can see what the default administrative distance values are of the protocol. You could see what redistribution is enabled on the protocol. If redistribution is enabled, if there are filters applied, you can see if filters are applied to the protocol, and so on. All right. So just something to consider. Just kind of a little summary of what we've been talking about previously. All right. What about route feedback? Route feedback is that concept in which I redistribute routes from domain A, for example, to domain B, and then somehow that route gets redistributed back from domain B back into domain A, right? And it's never really desirable to do this. We would never want to send a route back into the routing domain where it came from. And the diagram kind of describes this process. You know, routing protocols are pretty basic in their operation, the way that they work. They basically just try to find the best path to the destination. But in a lot of cases, especially with redistribution, we don't necessarily have a complete picture of the whole topology. In fact, we lose a picture of the topology based on the fact that the routes are being redistributed. The information that's being injected into the routing information through the redistribution process is really just artificial information. That seed metric is not generally representative of what the network looks like in the source routing domain. So it is entirely possible that a routing protocol could take the wrong path. In this diagram, for example, we see our topology. Sorry about that. So in this diagram, we're seeing here, we have a topology. We use EIGRP on, I guess it's router 1, router 3, router 4, and router 5. We're using EIGRP. And OSPF on router 1 and router 2 and router 5. All right. Now, if you look at the diagram, the path that is selected by router 5 that connects to router 1 is kind of suboptimal. All right. R5 will select the path, which basically goes from R5 to R4 to R3 to R1. And we can see that we got multiple serial links in that path, not because of the metric, but because of EIGRP's administrative distance. EIGRP has an administrative distance of 90, which is lower than OSPF's administrative distance. And we're talking about from the perspective of the 10110 subnet. If R1 is redistributing that route into OSPF, and R1 is originating that route into EIGRP, we'll always accept the EIGRP route first. And this is a really basic scenario, but clearly it's going to result in suboptimal routing. So we have to manipulate how the protocol, how router 5 interprets that information. And we can see we've created an access list that matches the 10110 subnet. In the EIGRP process, we've applied an administrative distance of 130. That's an arbitrary number. It just has to be anything above 110. So it could be 115 or 120. I think they chose 130 in this case because 115 is ISIS and 120 is RIP. But it doesn't really matter. As long as it's something higher than 110, right? And we're applying that administrative distance from the peer. The 10.45.1.4 address is the address of router 4, and the quad 0 indicates a specific match. And then the 10 at the end of this rule, this 10 here, is referencing access list 10. So we're saying, okay, if you're 10110 and this neighbor is telling me about 10110, I'm going to apply an administrative distance of 130 to that particular prefix. All right? The end result, of course, is that router 5 will prefer the OSPF route over the EIGRP route because OSPF's AD is 110, which is less than the artificially inflated AD of 130. All right? So that's just one example. We actually saw that example in one of our previous discoveries. Another is maybe invalid routing tables. Route feedback from a different routing domain could lead to some routing table or some invalid information in our primary routing domain. So it's possible, for example, that route feedback will preempt the original network advertisement, and it will essentially trick the routing table or the router to think, for example, that a particular route is more preferred from a different network. So in this example, R5, which is one of the routers that's attached to both routing domains, is feeding back the 10110 route back to domain A after it's been essentially removed by router 1. All right, so router 1 is advertising or originating that route. the 10.110/24 network into domain A. Router 3 then redistributes that route into domain B at the top. And then that gets redistributed back into domain A by router 5. If for some reason router 1 withdraws the 10.110 network from domain A, it is still possible for router 5 to advertise the route back into domain A even after R1 withdraws it. And because of that propagation, the route keeps the original route in the routing table for both domains, even though the network is not actually technically available. And this is what we refer to as an invalid routing table. Very easy to prevent this from happening, right? We did this in one of our discoveries. The best way is to have some sort of distribute list with prefix filtering, maybe an ACL or prefix list, or in the redistribution process, create a route map with route tags to make sure that we're not feeding back routes back into a routing domain where they came from originally, all right? So if I had tagged that route at router 3 and then created a filter on router 5 that said anything tagged with 3, for example, we're not going to include in the redistribution process back into routing domain A. All right. Another potential problem is routing loops, of course. Very similar to what we saw previously. Routing loops, especially if you have multi-point mutual redistribution, is a very, very common problem because we lose the overall path information, because we lose the original metric information. A downstream router might end up forwarding traffic to an upstream router and vice versa, which is going to create the loop in the topology, and then that packet will be processed through that loop until the time to live expires on that particular packet. All right. Especially when you are inserting routes with specific seed metrics. If you insert a route with an inappropriate seed metric, it makes the primary routing protocol that normally would be preferred over the secondary routing protocol not function correctly. So in this particular example, let's say the 10.110 prefix that's being advertised by router 1 was an external EIGRP route. So it has an administrative distance of 170, and it's an external EIGRP route. Router 2 may end up selecting the path to go to router 6 to reach that destination after router 3 and router 5 ended up redistributing that route between domain A and domain B. And this would cause this is caused by, in essence, a misconfigured or a malformed or poorly chosen lower seed metric being inserted by router 5 when it's redistributing the route back into domain A. And that seed metric provides kind of the reference value, if you will, to accommodate the routing for a particular topology. All right, so elevating the seed metric would make the path less preferred if it's compared to an identical route with a lower metric. So if only the path metric is used, in this particular case to identify the best path, we can modify the seed metric on R3 and R5 to a higher number than the source of the route on R1, and then that will make sure that router 2, for example, always selects router 1 as the source of the routing table, and that would eventually prevent the packets that are supposed to go to 10.110 from looping between domain A and domain B. All right. All of these scenarios are very, very specific scenarios that could potentially occur, but these are some of the common problems that you would see with redistribution, and you'll notice that in every one of these cases, we're always talking about redistributing on multiple points within the topology. If it's single point redistribution, you don't really have to worry about any of these particular issues. All right, the last one we'll talk about here is route summarization. Another possible problem that you could have is redistributing a summary would make sure that the primary domain continues to use a more specific route, right? What do they mean by that? They mean longest match routing is always preferred. Summary routes tend to have a shorter prefix than the individual routes that are included in the summary. So again, to prevent routing loops or suboptimal routing in this particular case, we could use route summarization. We still have connectivity, so the primary routes are still going to be used because they have a longer prefix match. And if those individual primary routes fail, or those individual longest match routes fail, the summary route is still being advertised. This particular diagram, you can see router 3 and router 5 are summarizing external routes in the 10.1.0.0/16 network, and the 10.1.1.0/24 network redistributes into domain B. We can see that listed here. The ASBRs advertise only the 10.1.0.0/16 network, not the more specific prefix. There isn't a conflict in domain A for this because the 10.1.1.0/24 is a longer match. That's going to end up going into my global rib, and then the 10.1.0.0/16 route, even though it gets fed back into domain A, isn't a problem because router 2 is always going to prefer the longest match, so it would still route to router 1 for the 10.1.1.0 network. If for some reason, the diagram doesn't really depict this, but if for some reason the 10.1.1.0 network was lost from router 1, but maybe it was sourced from a different location, we could still use that. Or if for some reason the 10.1.1.0 network disappears, but there are other networks within the scope of the summary, we could still reach that summary through router 6 or router 5 and so on. So again, you have to have an understanding of how route selection works in a particular routing protocol. And we talked about that throughout the course, right? We do longest match routing, we do lowest metric within a single routing protocol. We use administrative distance if we're trying to decide which protocol to use, given the fact that both of them are injecting routes from the same, or injecting the same route from different routing information sources and so on. So there's always kind of an order of operation about route selection. My suggestion, especially if you're doing this multi-point redistribution here, is that you investigate. We did that with one of our discoveries and a progression. You just check routes in one direction, routes in the other direction, and there's always going to be a unique solution that's going to be available to ensure that you have a stable environment. All right? So we'll go ahead and wrap up this discussion. We're going to move into section 9. We're going to look at a lot of the same mechanisms, the same controls that we normally would have, but we're going to do this in context of path control, policy-based routing, IPSLA, bidirectional forwarding detection, and so on. All right? See you there.